WIMSIG 2021 poster presentation. I am Ilknur Tulunay. I'm going to talk about the ST-metric measure spaces. Throughout this talk, I will be a unit interval. Define phi on the unit square by this function, x logarithm x over a x y, and y logarithm y over a x y. AXY is the average function of the points x and y. Geometrically, they are the midpoint of x and y. Phi x and y is a positive for each element in the unit interval, and it's also symmetric. These two facts are straightforward. This one is the triangular rule of the metric spaces, and this is not so obvious, and it has been proven by Adres and Schindler in 2003. Now define ST1 on the unit square by taking the square root of phi. By these facts, I and ST1 is a metric measures. It is a metric space. Now I would like to move from the unit interval to the n-dimensional unit cube. In order to be able to do that, I'm going to take Euclidean product. Now I would like to explain what is an Euclidean product means in general for any vectors, any metric spaces. So n here is a natural, positive natural number. We have n metric spaces, xi and toi. X is the product space, is the Cartesian product space. And taking Euclidean product means we are taking a square root of the sum of each matrix on the components xi and taking a square of that. So this is definition of taking an Euclidean product. And it's proven that it is an Euclidean, it's a metric space. So this is a metric space if we defined tau I in this fashion. There are other metric space, there are other product metrics as well. This is not the only one. For example, this is a theorem 161 of the book Metric Spaces or Circoid. And this is a metric, product metric. This is another product metric, for example. And we are thinking about the maximums of the values of each matrix. And that's called, let's call T max. And also if you sum it up, all the metrics in the components, then we will get another product metric. And let's call this product metric is tau sum. The theorem says that this inequality holds. Also, Circoid defines a conserving metric. Conserving metric is any metric day satisfying this condition. So in his book, Metric Spaces or Circoid, conserving metric is an important concept and it has a great usage. Now let's have a look at the example of this. For the usual metric spaces, the usual Euclidean metric, if we take DE, I denoted by DE, as the absolute value metric in the real line, then we can extend the real line to the n-dimensional real vector spaces by taking this Euclidean product. And then this give us the usual Euclidean product space on Rn. Just to remind you, the Euclidean product space, usual Euclidean metric, corresponds to L2 norm. Now get this idea and move to ST case. So if I take the ST1 and square, so ST1 for each component of I for this Cartesian product space, and then square it, sum it up, and square root by taking Euclidean product, basically, I obtain another metric, and this metric will be a metric on the n-dimensional unit cube. Also, we can talk about ST max and ST sum. Then this equality holds for the ST metric as well. Now let's have a look at some facts about ST metric spaces. Now, before that, I need to recall the definition of an open ball in a metric space. If we have any metric space X and D, open ball is defined as a set of, this is an open ball with respect to the metric D, center X, and radius R, consists of the points such that the distance between X and Y should be smaller than R. So that is my notation that I'm going to use. So these are the facts that I managed to prove, and these facts can be extended from the unit interval to the n-dimensional unit cube by taking the Euclidean product. So ST1 is smaller than or equal to absolute value. This is always the case for each X and Y between 0 and 1, except the 0. So this is an open interval in this here. So 0 is included. So this one gives us an upper bound. This one inequality is a lower, but it's not a lower bound because there's epsilon depending on an X and Y. So this is 2 square root of 2 epsilon, absolute value X minus Y, and ST1 X and Y, but this time I can take off all points on the unit interval. And by using these inequalities, we can prove that the balls with respect to the usual Euclidean metric is inside the balls of the ST metric. On 0, 1, and 0 is not included. If the radius is bigger than the log 2, then the Euclidean ball is inside this ST ball. If R, the radius, is smaller than or equal to logarithm 2, then ST ball is inside the Euclidean ball. So these will help me to look at the equivalence, the topological equivalence or uniformly equivalence concepts. That is the next thing to do. So what are they in general? Topological equivalent. So you have the space X and you have two metrics on it, D and E. They are topologically equivalent if they induces the same topology. As usual, if we have a metric, the topology induced by the metric is just the open balls, is the open sets of that topology. Uniformly equivalent if they satisfy these two conditions. For each epsilon, positive epsilon, D is smaller than epsilon, then there exists a delta such that EXY is smaller than delta and other way around, and this needs to be hold for each X and Y. If these two holds, then these two spaces, these geometric spaces, is uniformly equivalent. Lipschitz equivalent if these two conditions satisfies, there exists a K positive real number satisfying this condition, and this is a Lipschitz condition, and there is another K prime for other way around, and if these two holds for each X and Y, we have Lipschitz equivalent. These three equivalent concepts, Lipschitz equivalents are the most strongest one. If we have Lipschitz equivalent, then it is uniformly equivalent, then it is topologically equivalent. So the existing implication comes from this side to this side. So what is the case for ST metric? Again, I managed to prove all of those and on the unit interval, and then extend to n-dimensional unit cube by taking the Euclidean product. So ST metric is topologically equivalent to the Euclidean metric. ST metric is uniformly equivalent to the Euclidean metric. But ST metric is not Lipschitz equivalent to the Euclidean metric. I'm also managed to prove this. If we exclude the 0 from our interval, from the unit interval, then ST metric is Lipschitz stronger than the Euclidean metric. This is coming from this inequality, basically. So these are the facts about the ST metrics and the equivalences of it. Another fact about the conserving metric and the Lipschitz equivalence, every conserving metric on the product space is Lipschitz equivalent to the Euclidean product metric. Okay, and this implies that the ST metrics, the ST metric is Lipschitz equivalent to this metric and this metric. In general, if this is an usual Euclidean metric, it is equivalent to Lipschitz equivalent to T max, tau max, and tau sum. In my case, is ST metric Euclidean product here is equivalent to ST max and ST sum. This is a fact too. Now let's have a look. My main interest, I want to make the ST metric to a metric measure space. What is a metric measure space? We have space, a metric, and a measure. The metric space should be separable, and the measure should be non-trivial, locally finite, Borel regular, measure on X. Locally finite means the measure on each ball is finite. Borel regular means if the set is included in a Borel set, their measures should be the same. Before move on, I need to have another proposition theorem about the consistency, basically. So we have a unit interval, an ST metric defined on the unit interval, and then we can move on to the n-dimensional unit cube by taking the Euclidean product. And we have the corresponding topologies by taking the open balls as an open set of those topologies. So from topologies, by taking the product topology, we have the topology of the Cartesian product space. However, this should work in a sense that this should commute. For if I start from here to here, should not differ from starting here and coming to here. So what it means, basically, I need to prove that the topology of STN is the product, n times product of topology of ST1s. And this is true. It is not obvious, not surprising in a sense that this holds for the Euclidean case that we know in general. So I apply that, the idea of the proof in this case needs to be checked before we move on to the other facts about the ST metric. Okay, other topological facts that I need to prove, more facts on the unit ST metric. Again, these facts can be extended from the unit interval to the n-dimensional unit cube. ST metric is connected, compact, complete, and separable. This ticks off the first requirement of the metric measure space. What is the next requirement? I need a measure mu. So if I take mu as the measures of the defined on the open balls. Then this is from the book of Federer on geometrical measure theory. That's the definition is coming from that book. So if we define the measures on the open balls, we obtain a spherical measure. And the spherical measure is by definition unborrowable, regular, and locally finite. So all these will give me the result that I want, that the unit, n-dimensional unit cube, ST metric, and the measure defined on the open balls, defined by the induced by this ST metric, is a metric measure space. So why and what is the next thing to do? Why I am interested with this particular metric measure space? That is the next thing that I would like to explain a little. So the next idea is that I want to study Sobolev spaces of the functions defined on these metric measure spaces, and then look at the solutions of the differential equations. I expect some advantages. Right. And I want to explain too why I am expecting some advantages of calculations of finding the solutions of the differential equations on this particular metric measure space. Here is the experiment, or here's a little example. So this is a unit square. We have the diagonal points I denoted by the red. So 1 over n, 1 over n, 1 over 2 over n, 2 over n, and so on. And GK, the green ones, is again all of the diagonals except in the point that k over n. I'm adding the epsilon. Epsilon is a very small positive real number, and I'm adding it in that point. And for the blue ones, I'm subtracting in there. And then I'm going to look at the ST metric on this, the red line, red discrete line, and a green discrete line. And I'm going to look at the ST metric of the red and the blue and compare what are they saying, the number. So what I'm saying is that I'm looking at the ST metric on the basically this is a set of points, and Cartesian product of a set of the points. Only the k point, I'm adding an epsilon. Here I am subtracting the epsilon. These two values are not equal. This value is always smaller than this value. If you looked at the Euclidean Euclidean metric, they are the same. And a similar thing, if I change the location, or basically the timing of fluctuation, for example, K and L differs. This is positive, this is negative, this is always smaller. So L is bigger, so the timing close to the recent times gives you a smaller value in ST metric than the historical ones. This does not differ in Euclidean metric spaces. They are the same. This is a surprise. And this is one of the intuition that gives me that ST metric spaces is worthwhile to work on. What I'm saying is basically ST metric spaces includes the fluctuation structure in itself. Why? Well, the definition of ST metric is closely related to the entropy, right? So this is x log x is an entropy. So this is a relative entropy with respect to the midpoint. That is another relative entropy with respect to the midpoint, and I am symmetrizing these two and taking the square root of it. So ST metric is pretty spatial for that reason. And I believe that if by studying the Sobolev functions and the solutions of the differential equations on this particular metric measure space might give a better results. Thank you very much.